So we are Volta Recovery Systems, and this is a basic presentation on our material recovery process that we will use to recycle lithium-ion batteries. So our mission is to use succinic acid leaching process to basically, as just a small reaction kind of experiment that we intend to industrialize in the future, with the benefits of sourcing lithium and cobalt sustainably and ethically, and basically creating a solution that's environmentally preferred to current industry standards, as well as developing a profit-based model.
So what is a lithium-ion battery? Well, lithium-ion batteries are all around us in many different goods. First, as we can see, they're in electric vehicles that are becoming more and more prominent in our society. Next, we see them in things like our AirPods, and in the thing that we all carry around with us at all time, our iPhones. So how exactly do these batteries work? Well, a lithium-ion battery is made up of 4 parts: a cathode, anode, electrode, and a separator. The anode and cathode store lithium. Positively charged lithium ions travel from the anode to the cathode, and vice versa. Movement of lithium from the anode creates free electrons, which create a charge in the positive current collector. Electrical current flows through the collector, through the device being powered to the negative current collector. When charging, the opposite happens, and lithium ions travel from the cathode to the anode. So what happens when these batteries die and can no longer be charged? What do we need to do? So this is our motivation. As we can see here, this is an area where lithium is mined, and harvesting of lithium can lead to infected and exhausted bodies of water for local areas. This harms local ecosystems, as well as local communities who have decreased access to drinkable water. In the second picture, we see a mine in the Democratic Republic of Congo. About 3.4 million tons of cobalt lies in the Democratic Republic of Congo, and an estimated 40,000 children work in the Democratic Republic of Congo under highly unsafe conditions, resulting in many injuries and deaths. And in the US, we see that a fire is caused in a landfill by lithium-ion batteries. Only about 5% of all lithium-ion batteries in the US are recycled, so most of them end up in landfills. So proper disposal consists of sending spent lithium-ion batteries back to the manufacturer. This helps avoid fires from improper waste management, which may cause many emissions. And LIBs and landfills can also leach into groundwater supplies, as we saw in the earlier slide, contaminating local water sources. So what are some of the current practices to get lithium and cobalt or reuse them? So this first picture is of a solar grid. One great technique that is being researched now is the reuse of depleted batteries in the electric grid. Only about 20% of power in these batteries is used before they're considered to be depleted. So there's still 80% of the power to be used, and many companies are looking to put these batteries back into the solar grid electrical system to be used for our power every day. The problem is all of these batteries are different, so that's pretty hard. The second way that we can find these materials is just mining them. And obviously, as we saw from the earlier slides, this is very unethical and extremely environmentally unsafe. So this is not our best option. And lastly, we see that the Department of Energy invested $15 million in this startup ReCell. They're looking into things like direct cathode recycling and other material recoveries. But the problem is that these are extremely early in their experimental cycles. So these practices may not be industrialized for a while.
So how does our process improve on the current practices? So what we do is take lithium ion batteries and separate the cathode from them into a pure powder known as lithium cobalt oxide, which is crystalline in structure. We then put this powder into a batch reactor system with succinic acid and hydrogen peroxide. Well, hydrogen peroxide isn't in the main reaction equation we showed you earlier. Basically, what it does is reduce the cobalt's oxidation state in the lithium cobalt oxide molecule, making it more likely to dissolve in the solution. Then, as we put it in the reactor and allow it and stir it and allow time to pass, we find that the concentrations of the compounds containing lithium and cobalt actually increase, and that succinic acid concentrations and lithium cobalt oxide concentrations decrease. And what's useful about this process is that we've essentially separated the lithium and cobalt out of the lithium and cobalt oxide into compounds that can be used to actually reform the lithium ion batteries. So in conclusion, this technology will allow us to take batteries from common products like consumer electronics and electric vehicles, turn them into a reactive material, put them in our batch reactor system, and be able to make new lithium ion batteries, which can then complete the cycle and be used in these common products we see in our everyday lives.